Let's see, a few things. So we handed out the programming assignment to everybody. It is due next Wednesday. We handed out the written homework for everybody. That is due Monday. So I will try and make myself available for questions at some point before Monday in case you have questions about the homework. Because you asked me to, I posted a PDF of the schedule on the website. So all the class times are listed. And I posted all of the assignment deadlines on that schedule as well. So all in one place. There's when classes are and when assignments are due. Okay. Is there anything that you need me to do for you? Any questions about when assignments are due or anything like that? Everybody's okay, other than it being very hot? Okay. Okay. So I've been tourist. Young and I were performance debugging assignment 1 for the Palace. Okay, so here is the first question of today. In your homework, you need to use this programming language called ISPC. And so for some of you, it may be the first parallel programs that you have written. Now, this is the example that we had on the class last time. This was the same program that I talked about all last class and the day before that. So this is a program that that computes the sign of all of the numbers in the input array X. So here are 2 questions that will check how well you understand how this code maps to an Intel machine. So first of all, if I run this program, will it run on 1 core or will it run on multiple cores? Who thinks it will run on 1 core? Raise your hand if you think it'll run on 1 core. Okay? Who thinks it will run on multiple cores? No. Okay. Oh, okay. So the people that think it is 1 core are correct. This is a program that runs on only 1 core. Now, we know that this is a parallel program. So here is the question is, if I look at this program, it says for all the elements in the array, skipping by the number of program instances, compute the sign of that number. And there's another loop here because it's an iterative sequential algorithm to compute the sign. So, this is a parallel program. It only runs on 1 core, but when it's run, it will run in a SIMD way. So where in this code is there the parallel loop? Where in the code does it say that something should be done in parallel? Oh, yeah. You can't answer the question. So this is a loop. This is a loop. Are either of these loops parallel? Who thinks this loop is parallel? Right, some people think this loop is parallel. Who thinks this loop is parallel? Nobody. Okay. So good in that this loop is not parallel. Correct. This is just a regular for loop. But this is also a regular for loop. So why do you think this one's parallel? Both of these are just regular for loops. So the answer here is that neither of these are parallel loops. This is a program that's run completely sequentially by one of the program instances. It runs this for loop sequentially, skipping elements. And inside it has a nested for loop that runs sequentially for every term in the Taylor series. So where is the parallelism? This program will run in parallel in ISPC, but I don't see any parallelism here. Where is the parallel? If I know where the parallel loop is. The parallelism happens when I call the ISPC function. So I'm running a single-threaded control. When I call the ISPC function, that's like creating multiple instances of the function and running 8 instances of the function, or in your assignment, 4 instances of the function, because we set ISPC to do 4 wide set instructions. This would be true if we used ABX instructions. So once those 4 or 8 or multiple program instances are running, they're all running, but they all carry out this logic completely sequentially. And I get parallelism because I'm doing 4 copies of this. So there's no parallel code here. This is a no, like if I got rid of all of the red letters, it would be valid regular C code. I just happen to run it 4 times, and each time I run it, the value of program index is different. And all 4 of those happen to be running simultaneously and in parallel. Okay. So that's something you want to keep in mind when you're thinking about your ISPC code. Okay, so we are now at the end of the first week, and we have almost completely only talked about how hardware works. We haven't talked too much about how to write good parallel programs. So today I wanted to give a whole lecture on thinking about how to write pretty good parallel programs. Okay. So the process that you will go through is pretty much the same every single time somebody gives me an algorithm or gives me a program and asks me to make it faster. Every single time one of my students is trying to parallelize something, they will think about this as well. And it seems like we always go through the same steps. You know, step 1 is always identify what can be done in parallel. What are the pieces of work that can be done in parallel? And then break the problem up into a bunch of those pieces. And then figure out how to assign those pieces of work to various threads or various workers. And the goal in breaking all this up, remember, is of course to achieve some speed up. If I give you 4 processors, maybe I hope that you could get close to 4 times faster. Okay. Now, I'm going to be a little bit sloppy with some of the words that I'm using because computer science is very sloppy with the words that it uses in this case. So you can think about this process as you start with some problem to solve. And I'm going to break that problem up into a bunch of small subproblems. Now the words that people use can be very confusing. So someone might say, we're going to break it up into many tasks, or many jobs, or many. So I think about whatever the word you like to use. I think about it as, I break a big problem up into many things to do, many pieces of work. And then I need to assign that work. To run that program, I need to assign work to workers. Right? And those work, you might think about a thread as a worker, or you might think about a processor as a worker. But the easiest way for me to think about it is I have things to do, pieces of work, and I need to intelligently, I need to smartly assign them to workers. And then at the end of the day, I need to sort of assign workers to the actual pieces of hardware, to the actual execution context. So the first part of this is what, I want to talk a lot about the first 2 of these today. So let me talk about this first part of breaking a problem up into a bunch of small pieces. Or another, if I use a different word, decomposing the problem into a bunch of small pieces. So the main idea here is, if I have a processor with n cores, well, I better at least find n pieces of work to do, otherwise all of my workers cannot be busy. We will have a situation like we had up here on the first day of class, when one of the students was adding up all the numbers, and the other students were waiting on him to finish up all the numbers. So the key challenge is to try and figure out where that parallel work is. And it can be surprisingly hard sometimes to find parallel work. And there's a formula that is called Amdahl's law. And a lot of people joke at CMU about this not really being a law. You know, like Newton's law is a law. It's very important. Amdahl's law is a very simple equation. It does not rise to the same level of sophistication as the law of gravity or something like that. So, but let's think about this a little bit. So, let's say that you have a program, and some small fraction of that program is sequential. You cannot parallelize it. You have to do things in a particular order. And let's say that that fraction is called, I'm going to use the variable s. So S stands for sequential here. So let's say if 50% of your program cannot be parallelized, S 0.5. So the math says that, well, if S is the fraction of your program that cannot be parallelized, even if you do a perfect job on the rest, you're never going to be able to exceed a speed up of 1 over S. So let me show you a picture to make this more clear. So I'm going to use an example from some work that some of my students do on image processing. So imagine you had an image, a photo, and let's say it's n by n pixels. So there's n squared pixels. And I'm writing some application that's like a, that edits the photos on my phone. Now what I want to do is I want to double the brightness of all the pixels. And then I just want to compute the average of all the pixels. I want to add them all up. So for example, your phone does this all the time when it's doing automatic exposure. It's always trying to figure out if the image should be darker or lighter. It's often looking at the average brightness of all the pixels to compute what that should be. So down here, I hope you can see it, I've drawn how that program runs, where this is time, and this is how much parallelism there is. So if I have a sequential program, it's always 1, and it takes 2n squared units of time to complete the program. 2n squared because step 1 takes n squared. I touch all the pixels. And step 2 takes n squared. I have to touch all the pixels as well to compute the average. So does everybody understand this picture here? It's at 1, because there's no parallelism, is length to n squared, because that's how much work there is in the program. Now let's say that I parallelize the first step in this program. Because it's pretty easy. I just need to double all the pixels. Pretty easy to parallelize. I know how to do that. So if I parallelize the first part of this program, my picture will change to look like this. It'll go from this, where everything is sequential, to the first part has P processors, perfectly parallelized, and now has time n squared over P. Because I had n squared work, and it was perfectly parallelized onto all the processors. So what is the speed up that I have achieved here? What is the maximum speed up? Like imagine that if I had a really large number P. Let's say I want to run this on a supercomputer. P is 10 million. So this bar goes to 0, and my speed up, the time is 1/2, so the speed up is 2. So very simply, if we see this in math, the speed up is the time it took before, time on one processor, 2n squared, divided by the time on P processors. So the time on P processors is n squared, the sequential part, plus n squared over P, the part that I parallelized. And as P gets very big, this term goes to 0, and the speed up is 2. Okay, so if I wanted to do any better, if I wanted to get greater than 2 speed up, what would I have to do? Because right now, S, the sequential part of my code, is 0.5. I have to somehow figure out how to make this sequential portion more parallel. And do you think can I compute the average of a bunch of numbers in parallel?
Yes.
Yes, I can. It's not too hard. In fact, you basically did it on the first day of class. So if I make it parallel, let's just say that I have every one of the P processors compute its own sum, n over P of the sum. And then I'll add up those P numbers to get the final result. So now this went to n over P. But there's still a little bit of P here at the very end. Because every processor computed n over P elements. I had P intermediate results. And then let's just say I use one processor to go I equals 0 to P sum on. So I'm doing pretty good now, as long as P is not too big. And it can be very surprising how bad this can be. So let's think about this. So here what I did is I plotted a curve. And my curve is the maximum speed up as I change the number of processors. So the x is number of processors. So it goes from 1 processor to 64 processors. And this line here is how fast the maximum possible speed up if s is 0.1. And this line here is the maximum possible speed up if s is 0.1. So if 10% of your program is sequential, 10% of it you can't think of an algorithm to parallelize. That might not seem like very much. You're like, oh, it's only 10% of the program. Let me start to work really hard to parallelize it. If you do a perfect job parallelizing it on 64 cores, you're only going to see maybe 6x speed up. So you did a beautiful job with a parallel algorithm on 90% of your code, and you only get 6x speed up. If 1% of your code is sequential, you're still only going to get 40x speed up on 64 cores. And now imagine what these curves might look like if we have to run this x-axis from 64 processors out to 10 million processors, like on a modern supercomputer. So essentially, 99.99999% of your program better be parallel, or you might as well not think about running it on a big parallel machine at all. So in this class, almost all the time, it's going to be your responsibility to figure out how to decompose an algorithm into parallel pieces of work. And there have been many researchers for 10, 20, 30 years have been working on compilers that try and look at your program and automatically break it into parallel pieces. And still to this day, we have not been very successful for very general programs. Like there's no compiler that can take a look at your C code and automatically come up with a good parallel algorithm from the sequential. Many papers have been written, many people have tried, but I would say it's fairly accurate to say that compilers are not very good at parallelizing your code yet. So that will be something that you have to still worry about in this class. Now, once you've figured out how you can make almost all of your program parallel, and you have all these different pieces of work to do, we need to think about how we're going to assign them to those cores. Or in other words, if I use various different ways of saying this, I need to think about how to assign work to threads. Or I need to think about how to assign work to workers. And the goals of that are to balance the workload across all of these workers. So if you remember on the first day of class, we had a problem where I gave different people different amounts of work, and it resulted in poor speed. And they came up with a good solution so that everybody had the same amount of work. And that solved the problem. So if you are responsible for figuring out how to break up an algorithm into pieces, who do you think is responsible for assigning those pieces to various threads or various cores? Is that your responsibility as the programmer? Or does the compiler do that, or do you get help with that? So let's think about our one example from last time. Actually, I'll give you two examples. This is the code from last time. Same code as the beginning of the lecture. And then also last time I said, well, if you don't want to write these complicated for loops, you could just use for each. So on this side, the programmer has manually, himself or herself, assigned work to ISPC program instances, which are the workers that do the work. So in this case, what is the work? If the workers are my program instances, what is the parallel work to do? What is a piece of work? Yeah.
To compute a sign of a specific value?
Yeah, so this program, the programmer has said, look, I can the whole problem is to break up an array into a whole bunch of elements. So the individual pieces of work are computing the sign of an individual element. We have, in this case, 4 workers, 4 ISPC program instances. So just like we had on the first day of class, we have a question, well, which workers should do which elements of the array? And so in this program, I said that worker 0 was going to do array element 0, 4, 8, 12, 16. Worker 1 is going to do 1, 5, 9. In this program, I didn't make that decision anymore. I used for each. And so in this program, I said that, hey, the work is still the same. The worker, all these iterations of this for loop. And I said, I don't care what worker does every one of those iterations. ISPC, you can go figure it out yourself, and I trust you to do a good job. So the program on the right, the assignment of work to workers, is done by the compiler. On the program on the left, the assignment of work to workers is done by the programmer. So the assignment can be done in many different ways. Here's another example. So did anybody look at the code I put online on how to create threads? Like I put like a little example of how to create threads. It looks kind of like this. So here's a program where I'm running SINX, but I'm not using ISPC. What I'm doing is I created one thread, and I created a second thread. So what is the assignment of work to the workers? So in the previous slide, the workers were ISPC program instances, right? On this slide, what are the workers? They're C++ threads, exactly. And I have 2 of them. So I have to assign all of the elements to one or the other thread. And how did I do that? Well, I did that by what arguments I passed to those thread constructors. So the thread that I created is assigned the first half of the array, and the thread that was already running works on the second half of the array. Now, let me give you one more example of assignment. So in your homework, which is in part 3 of the programming assignment, we talk about, you're expected to learn about a way to create ISPC code that runs on all of the cores in the machine. So, and it is called you create tasks. So it's almost like the same language from this lecture. So what this code does, and you will learn in your homework, is that it says, I want to create 100 different tasks, 100 different pieces of work, and ISPC, I want you to do all 100 of these things. But I have a computer that only has 4 cores. I can easily also say, I want you to do these 1 million things. So here's a question. How does ISPC assign all of these tasks, all of this work, to those 4 cores? So one answer might have been, well, if I want to create 100 pieces of work, maybe I should create 100 threads. I could create 100 threads and give 1 piece of work to every thread, and then I can just let the operating system figure out when it wants to run those threads. That would be one solution. So I did that. Let me go to my code here. Okay, so here I wrote 3 programs. What this program is supposed to do is it's supposed to do, it's not 100 things, it does 1 million things. Okay? And so it creates 1 million tasks, so 1 million pieces of work. So in this case, the task is really, really simple. The task is do nothing at all. So my first program is not a parallel program. It's right here. So test 0. So test 0 says for I equals 0 to num tasks, call function worker1, and worker1 does not do anything. It does nothing. Okay? So everybody understands that program. That was really easy. Now I have a second program, test 1. And what test 1 does is for every single task, it creates a pthread for that task. And the pthread does nothing, and then it terminates. So that one's really easy too. And then the last one is I create, it's even more complicated, I create 1 thread for number of workers. So I only create a fixed number of threads. And so on this computer, which is a 4-core hyper-threaded computer, if I wanted to use the machine really well, how many threads should I create? If I wanted to have a thread on every execution context, I need 8 threads. I need 4 cores times 2 threads per core. So I set num worker threads, we'll see in a second. So what I do is I create 8 threads. I spawn them all. I create those threads. And what the threads do is there's a single shared variable called total number of tasks, which is set to 1 million. So what the thread does is the thread works in a while loop. It says, give me the next task. And it gets the next task by incrementing num thread data next task plus plus. So for those of you that care, next task is a shared variable across all the threads. So the way this works is that every thread goes to the shared variable, says what is its value. If the value is less than 1 million, it increments the shared variable, and then does a task. And when it's done, it goes back to the shared variable and says, can I have the next one? And so together, all 8 of these threads are incrementing the shared variable and then calling the worker1 function. Okay. So the first version of the program spawned no threads at all, and essentially just called the 0 function. The next version of the program spawned a thread for every single task. And the last version of the code created exactly the same number of workers as you have processors on the machine. So let me go ahead and run this thing for you. Okay, and I'm gonna, okay, so it's running. So first of all, test 0 already finished. It took 0.05 milliseconds, which makes sense. I called 1 million functions. It doesn't take very long. If you notice, program 2 is still running. and program 3 finished immediately. So let me look at these results. So can you see this thing right here? Okay, so thread 0, or sorry, the first program only had one thread. So it had no communication, no problems. It just incremented the number 1 million times. Notice that. The second thread spawned 1 million threads. Or sorry, the second program spawned 1 million threads and took 17 seconds. And then the third program, which only spawned 8 threads, but they all worked together, took 0.4 seconds. So the second program, like creating only the right number of threads, was 419 times faster than creating a thread per task. And no parallelism at all was actually 800 times faster than that. So this is an interesting example of saying, first of all, if you don't have a big problem, if you're not having a lot of work, it makes no sense to parallelize anything at all. The second thing to learn is that spawning threads is expensive. And so typically a good program will only create about as many threads as there are processors on the machine, or execution context on the machine. And the threads will work together to organize who does what. And if you look at this printout says, well, how many of the tasks were performed by each of my 8 threads? You know, there's a little bit of randomness in there. It wasn't exactly equal, but it's pretty equal. Pretty good workload balance. Okay. And the last example that I had where the threads are all, yeah.
Can I have a question?
Yes.
Is the code similar in different libraries or languages that support creating a thread?
Well, it depends. So I was creating P threads there.
Oh, yeah.
So I was creating the real operating system kernel threads.
Right.
So that'll be about as fast as it can be to create an operating system managed thread. I mean, think about it. I have to trap into the kernel, I have to interprotect it, and I have to do a lot of things in the operating system. Now, something like Silk is not creating threads.
Right.
Silk is creating tasks and putting those tasks in a task queue. So Silk will be implemented very much like my program 3. So what you saw in my program 3 is what a good system will do. And you saw in this result, it was 420 times faster. So 420x is a pretty big difference, especially when I'm only hoping to get 8x from parallelism. Okay. So, and the last, somebody has to choose how to take those threads and map them down into actual hardware execution contexts. And that's stuff that we usually don't worry about too much as the programmer. Like I created those 8 threads, and I just expected the operating system to use all of the execution slots on the machine. And of course, you know, the operating system is not stupid, so it did. So mapping the workers to hardware is something that usually someone else will do for you. Like the operating system might map threads to execution contexts. Or the compiler might map program instances to an ISPC. What do program instances map to an ISPC? It would be lanes in a SIMD instruction, or elements of a SIMD instruction. And so there are some interesting decisions if you make the wrong decision about how to map threads to the hardware. And you all answered this question well last time. Last time I actually asked you a question about how to map threads to hardware, remember? I said, well, what happens if we have 2 threads and we have 2 cores and 2 execution contexts per core? And you said that we should put 1 thread on this one thread on this core, and another thread on this core. And what was the reason why that was a smart idea? Why, if we only have 2 threads, we have 4 execution contexts, but we chose to place the threads, or the operating system chooses to place the threads on different cores. Why would I expect better performance with that decision? You got that answer right last time. Does anybody remember? In fact, let me show you that that's the right answer, because I have another program. My other program does this. It does nothing interesting. That's why it's called PEG CPU. And PEG CPU, okay, so what it does is it creates, run test, it will create num threads, and then complete, and each thread loops for millions and millions of times. So it's very expensive. So let's run this program. And CPU, and I'm going to give it how many threads I want to run. So let's say I want to run 8 threads. And what I have open over here is my CPU monitor, which tells me how busy those threads are. So first of all, quad core hyper-threaded. The Mac operating system is telling me I have 8 virtual CPUs, which makes sense, 8 execution contexts on the processor. If I run this program, look at what happens. I have 8 threads. The hardware has the operating system has placed all 8 of those threads on the processor. The program is done now. And you see all 8 of those threads working really hard. Makes sense, right? Let me do it again. I'm now running 8 threads, and I'm completely using my CPU. Okay. So if we would assume that that's core 0. This is hyperthread 0 on core 0, hyperthread 1 on core 0, core 1, core 2, core 3. If I run 4 threads, what do you expect to see? Well, if the operating system is smart, it will schedule the threads in the same way that you recommended last time. It will put 1 thread on every core. Now let's see if it does that. Yeah, it does. Now what would happen if you saw only these 4 being used? That would mean that the processor was leaving core 3 and 4 completely empty and having 2 threads share the resources on core 1 and core 0. That would be not so smart. And you can see that the modern operating system knows how to do this just like you do. Okay. So I'll put those programs online. Okay, so let's start talking through an example. And we'll start talking about how to think about a little bit more sophisticated parallel programming problem. And here's the example. So this is more of a supercomputing example. So imagine you have a big grid, and you're trying to do a large simulation. So this is going to be true of something like weather simulation. This would be true of climate simulation, or a simulation that's trying to model fluid flow over a jet engine or something like that. And you don't need to know anything about the math, but you only need to know how data is accessed. So imagine I have a grid, a matrix, and I'm storing values in this matrix. And the computation that I want to perform is the following. Is I want to, for every element, which I'm going to call Aij, I'm going to compute its new value as the average of its 4 neighbors. So Aij equals sum of the one itself, one above, one below, one left, one right. Okay. And this is, if you like image processing, this is kind of blurring the image. Basically taking any kind of high frequency and blurring. So if I give you the whole piece of code, here's the whole piece of code written in kind of C. So while we are not done, I'm going to iterate over the entire matrix, performing this update. So for every ij, back to here, for every ij, perform this update, which is this code right here, is just that code there. And as I do this, the values are going to get closer together. They're going to get, like, the values next to them will be more similar. And so once they become similar enough, this update, things will stop, the values will stop changing. And so when they stop changing, that's when we will stop the algorithm. So for every time we do an update, I'm going to compare how much it changed. So previous, new value, take how much it changed, and add that up. And if all of the matrix does not change enough, so if diff is less than some number, we're going to stop. We're done. So it's while not done, through the array. If not done, do it again, and so on and so on. Okay. So here's my question. Where are the dependencies? Or in other words, which loop, can we parallelize any of these loops? This is your code. So somebody, you're shaking your head no. That's correct. So why can't I parallelize these loops? So can I run the iterations of this loop in parallel? No. What tells you that I cannot? What about the code is telling you that I cannot? It's the fact that when aij gets written, the next iteration over, it will use this value. And so if I had to draw this as an image, the dependencies look like this, right? So we update this value, but this value is used to update this value. And this value is used to update this value, and so on and so on. So this program is very sequential. Can anybody think of a way to run it in parallel? There is a way to run it in parallel. So these are the dependencies. Are there elements that do not depend on each other? Is there a way to run it in parallel? Well, what do you mean? So specifically, what do you mean? I can't move the grid, because the grid represents the ocean. I can't change it.
But I could use something next.
Yes?
And then
Yes? Does anybody, where is the parallelism? So if there is no parallelism if I iterate this way, that's correct. There's no parallelism if I try and iterate this way. Can't go parallel here. Is there some order in which I can process the dots where there is parallel? Ah, yes. So I can actually go this way. And then I can go this way. I can go this way. Now there are some problems with this approach. Now I could get parallelism like this, but there are some problems. So let me tell you about some of the problems. First of all, there's very little parallelism here. And there's more parallelism here. So for large parts of the algorithm, I cannot use many cores. So for large parts of the algorithm, if I have a lot of processors, many of the processors just cannot be used. And Amdahl's law says that if I have sequential regions, I very quickly run out of gas. Okay. So what can we do? I want to run this thing on a supercomputer. And the program has very little parallelism. Even in the best case, you were really clever, you figured out the best way to get the parallelism. There's just not much parallelism there. What can we do? One answer is we can go home, we can say it's too hard. Go home, it's hot in here, we don't go home to AC. Too hard. But the other answer, and this is often the answer in a parallel programming class, we will take a break and then we'll talk about the answer. Who figured it out? How can we make this faster? So the answer is we are going to cheat. We are going to change the program. I don't want to compute this anymore because I don't know how to parallelize it anymore. So what we're going to do is we're going to actually change the program to another program that computes about the same thing, but is much easier to parallelize. So something that you will find in many parallel systems problems is you look at the algorithm and you say, this is not parallel, I don't know what to do. A big fraction of the code is not parallel. I can work really hard, I can change all my loops, but it still will not help very much. So sometimes you'll have to think of what's a completely different algorithm that works, that is much better for parallelism. So if you were a scientist, and if you knew about numerical computing, you knew about solving differential equations and solvers, you would know about another algorithm which computes the same thing, but does so in a manner that's very easy to parallelize. So what I did here is I divided my grid into red nodes and black nodes. And so instead of going update all the elements with dependencies, I'm going to update all the red nodes based on the black nodes without changing the black nodes. And then I'm going to update all the black nodes based on the red nodes. So there are dependencies, but there are no dependencies as I'm iterating over the red nodes. There is a dependency before the next loop, but then again I have another parallelism. Now you might be saying, wait a minute, that's computing a different answer. And you're right, it is computing a different answer. But if I'm a scientist and I know how this algorithm works, and I know how the original algorithm worked, I might be able to say, hey, this new answer is good enough. Or, in other words, this whole algorithm was converge until you're run until you're close enough. So as long as we run until we're close enough, we'll say this is good enough algorithm. Okay, so that's not something that any of us in the room would have been able to come up with because we are not experts in this algorithm. Okay, so for the rest of the lecture, I'm going to use this new algorithm, which is completely in parallel, update all the red, and then completely in parallel, update all the black. If not done, update all the red, update all black. If not done, update all the red, all the black. Okay, so now we know how to decompose the problem. We're going to decompose the problem in terms of all the dots. Now we need to think about how to assign this work, which is processing one element, to our various workers, to our different threads. Okay? So let's think of two examples. One example might be, let's just split the matrix across the processors. And I'll put all of these rows on processor 1, all of these rows on processor 2, all of these rows on processor 3. Another answer might be kind of like what we talked about last time. Let me interleave the assignment of rows to processors. So think about there being 4 processors here. And let's say we divide these elements across all the processors. And then the processors have to communicate after every iteration of the loop. Because in order for me to know how to compute this black dot, I need to know the actual value of this red dot. So when the red dot is updated, this value needs to get communicated to the other processor. So given that, do you have an idea of which one you might prefer? So people are pointing to this one. So why would you prefer this one? Less communication, because for these cells here, there's no communication at all with other processors. Whereas every single node here needs communication. And that might be a good answer, absolutely. It's interesting that, remember, so last time I told you that interleaving was better when we were talking about ISPC. So you have to kind of know your machine to know what the right strategy is. Exactly. So if we consider, and you guys already got it, is if we consider what's happening, it's like update all the black, communicate, update all the red, communicate, update all the black, communicate. Then if we think about what processor 2 needs to read, processor 2 needs these values from processor 3, these values from processor 1, and only for every chunk of data that a processor has, every processor has to communicate 2 rows. Whereas in this example, every processor has to communicate 2 rows for every row that it has. So it's much, much bigger. So good. So now you're definitely starting to get the hang of this. Okay. So now I'm going to actually write this. We've talked about how to parallelize it. But now I'm actually going to write some code for this problem. And I'm going to write it in two different ways in this lecture. Because I want you to think about the problem in a couple of ways. So the first way is we're going to all think about it in a very data parallel way. And I'll tell you what that means in a second, or about right now. So we're going to talk about how to think about data parallel programming. So I said, when I described how we were going to do this, I said for every element in the array, we're going to process it. And really what I was saying was for every element in a collection, we're going to run the same operation. And for those of you that have had some kind of functional programming, that would be like mapping a function onto a collection. If you haven't had functional programming, don't worry about what I just said. It's like if how many people have written code in MATLAB? So a lot of people have written code in MATLAB. So in MATLAB, you think data parallel. You don't think for I equals 0 to n do this. You think add A and B to get C. And you're saying, I want you to do that one operation in parallel, or maybe not in parallel, but on all the elements in the array. I have a function, perform it on all the elements in the array. So you kind of have data parallelism in ISPC. In ISPC, you kind of have data parallelism in the for each loop. Because what you're saying, when you write a for each loop, is I have all of these iterations, and I want you to do the exact same thing for all of those iterations. It's kind of like a complicated MATLAB program. Now, there's no array here. So here it was, in MATLAB, it was like there's an array A and array B, and I want you to do the same thing for all elements of the array. Here it's a little bit different. Here it says there are n iterations, and I want you to do the same thing for every iteration. And what data is processed in every iteration actually kind of comes out of how you wrote the loop indices here. Right? So it's very explicit. So this is kind of a data parallel program. So you can kind of think about this loop body here as the function to do. And you can think about the for loop as defining the sequence of array elements that you want to do it. But in ISPC, so this kind of makes a lot of sense. For every element of the array, do something. But ISPC is more general, right? I can write this program in ISPC too, which is also a valid program. And what does this do? So this program computes the absolute value of every element in the array. This program does what? It computes the absolute value of the input, but then copies it twice into the output array. So I can write whatever I want in ISPC. It doesn't necessarily mean the input is the same size as the output. So it's a little bit more flexible. So this is also a valid ISPC program. It just happens to have more complicated arithmetic. Think about this program for a second. And I want you to talk to your friend a second, because this one's more tricky. Here's another example of, do you understand ISPC? Is what's going on in this program? What is the output? What does this program do? So take 30 seconds, talk with your friend, and see if you can figure it out. This is a little bit trickier program. And the key idea is, if I is greater, if xi is less than 0, we're going to do do something here. Okay, so what does this weird program do? If the value is less than 0, it writes the element shifted by 1. If it's greater than 0, it just writes the element to the output. So, is this program valid? Why? Okay, so some people are saying it's not valid. Why is it not valid? If I wrote this program in C, would it compile? Sure, it's valid. Does it have a well-defined answer? Absolutely. I run the program and that happens. But this, for each, the iterations are independent. And if you wrote for each, you told ISPC they're independent. You can run them in whatever order you choose. So now, if you have a positive value, right by a negative value, two different iterations might write to the same value. Now, in C code, if this is a sequential program, we know the result. Whichever is the later iteration will be the value in the memory address. But in this program, I cannot tell you what the answer is, because I told ISPC you can run these in any order, and I don't care. And the output of the program depends on the order. So this is a non-deterministic program, meaning that you could run this multiple times, and it would be valid to get different results. This is not good. So some people use there are data parallel languages that are much more pure. They don't allow me to access an array element. So let me show you, this is much more like MATLAB now. So here I wrote a program, and let's say that I have a data type, like a vector, or I'm going to call it a stream here because you can't, because it's not quite a vector. So imagine I have a collection of elements, a sequence of elements, and I'm calling it a string. And I have a function which takes two not vector inputs, just regular inputs. And in this pure way of thinking about it is if I call that function on a collection, the program will run this function on every element of the input and write the output, the output y to every element of the output. So now it is not possible, given this language, it is not possible for me to write a program like the one that I did here, because there's no such thing as accessing arrays. There is only accessing the inputs of the function. And the function is for you automatically executed on every element of these special types of arrays. So this form allows me to write more complicated programs, like, let's say for every element of input, process temp, create a temp. And then for every element of temp, write an output. So you can think about this as there being a collection input. It feeds through this function to get a new collection. And it feeds through this function to get a new collection. And so on and so on. So this is a very data parallel way of thinking. And a good data parallel compiler can turn this code into code that might look like this, which would be very efficient. For every element in the input of size n, run the first function, take the output from the second function, and then output into the final output array here. So these languages that are very constrained, they only allow you to execute a function on every element, allow the compiler to do some fairly fancy things. Yeah? cannot, given only the ability to run on every element. And if I wanted the ability to write shift left, I cannot right now. I cannot express that shift left operation in this language. Now, if I wanted you to do that, I would extend the language with new operators that manipulated an input stream and shifted it left. Or in this example, takes every element of the input and repeats it. So imagine if Yan wanted to shift left, I would have to add a new thing to my language which says, here's shift left. So almost all of these data parallel languages give you run for every element, and they give you a library of various operators that manipulate one sequence into another sequence. And you have to be clever about how to use those operators to get what you want. So this code, if you had this in your library, you could write a program that would be equivalent to this one that I wrote here. Yes?
So could we do some lazy operation?
To do lazy operations?
Yeah. Because while we complete a function and then another function, this is not big. So could we do some lazy?
You could do lazy. Or you could do both lazy, and you could do. Notice that this program never actually computes a temp. Like it never creates the full collection temp. So it's not lazy, but it's actually optimized in that the program only wants the output. So in this case, it takes as input the input array, and it outputs an output array. But even though logically there was this array temp never gets created. And you could potentially also do things, you could do optimizations that were lazy. I don't have one on my slides, this is not lazy, but it's a similar idea. Yes. So these data parallel languages constrain what you can do, but the compiler can do some fairly fancy things for you. One operator that almost everybody wants, and is one that I should tell you about, is gather and scatter. So gather says that I will give you two collections. I will give you an input array, and I will give you a list of numbers. And so I want you to make a collection by grabbing only those elements from the input array and making a new stream. So I can actually draw it for you. So if this is the input array, and these are the numbers, gathering from the input array using these numbers yields a new vector that's a subset of the original array. And so your computers, one of these SIMD vector instructions is in fact not just load a whole vector, but gather, which is a very useful instruction, which is it takes as input one vector of numbers, it takes a base pointer, and then it loads these offsets from that array. And scatter is exactly the opposite, which is given an array and a list of numbers, put the numbers back in the array in all these different places. So these are very, very important instructions that like every GPU has. CPUs currently only have gather. Is there an AVX scatter yet? I don't think so. Okay. So now that we know how to think about this that way, let's look at the grid solver example. So this is that grid solver, and now I've written it in a very data parallel way. Now I chose one of the data parallel languages where I actually can write indices. So it's more SPM easy. So while not done, for all red cells in parallel, do the update, and then compute the difference and add them into a variable. Now I used a special library function here called reduce add. Because remember, all iterations of this loop could potentially be running in parallel or in any order. So if they all just did plus equals to the diff variable, I have potentially a race condition. I have a problem. So any data parallel language, in the same way that it gives you gather, scatter, a library of operators, if you want to have communication, you will need to use some form of global operator. In this case, the global reduction is that global operator. So this code here is sequential. Everything inside the for all loop is run for every iteration. And then all of this code is completely sequential. So this code is written very much like how we think about this. I will say, sequentially, while we are not done, for all the elements in red, in parallel, update them. And then really, I should have put another for loop here for all the elements in black. But I was sloppy. So let's now think about how to write this in a slightly different way, maybe a little bit lower level. And I want to introduce the term a shared address space, because I haven't introduced that term in this class. And so what I'm about to talk about is probably how all of you already think about a parallel computer. Is that we have a bunch of processors, and we have one memory, and the processors can communicate with each other by reading and writing to the same address. So if I'm a processor, or I'm a thread, and I want to send a message to the other thread, I can say store the value into variable x at some address. And if another another thread wants to read that value, it can go check the exact same address or variable in memory, and it can get the value. So some people like to think about a shared address space as a big bulletin board. Like, if we walk in the hallway, there are on the walls, there are places where people post signs and people post messages. A shared address space is like, I can post a message, and then anybody else can read that message from that address space. So in this example, x is that shared variable. Thread 1 wrote 1 to x. If sometime later, thread 2 wants to read x, it can load that variable, and it will see that write. So that's exactly how you probably expect a parallel computer to behave, but that's what we are talking about right now. So in a shared address space situation, the threads interact by reading and writing to shared variables. In the data parallel way, the threads actually could not interact. There were no shared variables. The only way that the threads, all the workers performing this loop, could interact was through special library functions like reduce add or other library functions that Kayvon talked about. So when you learn more about ISPC, which is fairly data parallel in thinking, when you read the documentation, it will say, here's the library of functions that you have to communicate between the instances. Otherwise, there's no such thing as communicating between the instances. In a shared address space system, all the threads can access the same variables. And I won't talk about it in the summer, but if you took a computer architecture class, you would learn about all the different ways you can connect processors up to memory so that all the processors can access the same memory. And in many modern computers, how to design the network that goes between the processors is maybe the hardest part of the processing. So I'll give you like a little example here is if this was an Intel computer, where we have a cache and 4 cores, there's a network on chip that connects all the processors to those cores. In Intel processors, that network is actually a ring. It's very much like the ring roads in Beijing, because if you want to communicate with another processor, you have to send around this ring. In some other systems, every processor is connected to every other processor. And so not Sun anymore, Oracle's processors. Every processor is connected to every other processor, and it's pretty interesting. So is that these are the cores. This is an 8-core chip. And this is the network containing, connecting all of the cores right here. CCX stands for crossbar switch. And it's interesting that the crossbar, the network, takes the same amount of space on the chip as one of the cores. That's how expensive it is to produce an expensive network. And one of the reasons why we had to update your homework assignment yesterday after we released it is that the computers that you're running on are actually 2 CPUs. Each CPU has 12 cores, but there's actually 2 of them. It's like 2 CPUs. And so there's actually a network connecting those 2 CPUs because every CPU can access the memory of the other CPU. And so you may not know that, but sometimes if you load a value, the load value goes from this CPU over to here and then out to memory this way. So depending on what address you load, it will actually take a longer amount of time on a dual socket CPU. Okay, so back to our example now. Is remember the problem. Everybody remembers the problem. And now we have a problem. So in the data parallel version, we just said it's a sequential program. There's a for all loop where we'll run in parallel for a little bit. And when the for all loop is done, that means that all the workers are done and we'll proceed. In a shared address space system, we have to do all of that ourselves. You have to write that into the code. So if we think about how this works, is we want to do all this work in parallel, and then we want to wait until everybody's done, and then we want to do a bunch more work in parallel, and then wait until everybody's done. So we need to now start communicating and organizing all of these workers. And so I'm going to talk about 2 different ways to organize the workers. So first of all, I want you to make sure you understand the code. So unfortunately, it's a little bit messier now. So here's the code that you would write if you wrote this in threads in C++. This program is run by all of the threads in the machine. This is kind of like ISP, this is STMD style. So this program is run by all the threads in the machine. And notice that I get the thread ID. This would be like a program index in ISPC. And based on this thread's thread ID, the thread computes what region of the matrix it's supposed to compute. So it uses the same scheme that you said on an earlier slide. So thread 0 will do this part. Thread 1 will do this part. Thread 2, and so on and so on. So if you look at the math, it'll say my min is thread times, so n over num processors, or number of threads, this is n. So n over number of processors is how much each thread does. So my min is the row that this thread will start at. My max is my min plus the number of rows that every processor does. So my min, my max for thread 1 is min here, max here. And then the for loop says, while not done, while not finished, every step, so ignore the barriers for now, but for every step, for j is from my min to my max, update all of these elements. That's what the code's doing. And then there is there's some stuff we haven't talked about here yet with the lock, and then there's some barriers. So here's my first question. My first question is, why does every thread only iterate over a part of the array? That's because all the threads together do all the work, right? Okay, so that's an easy question. Now, this code does exactly the same thing. For the elements that it is responsible for, it updates all the elements, and it computes the difference, and then updates a single shared variable. So up here, diff, these are variables that are shared by all the threads. So every single time an element changes, we do diff plus equals change. Now I put a lock around these things. So how many of you have seen a lock before? I'd like to know, because I'm about to explain it. But have any of you used the lock? So you've used the lock, not everybody, so let's go ahead and talk about it. So what this lock says is it only allows one thread to have the lock at a time. So this is a variable that when you call lock, when a thread calls lock, when lock returns, the thread is guaranteed that it is the only thread with the lock. So imagine I had an item. Let's say I had a very important item. Let's say my iPhone. Only one of us can have the iPhone at once. So if you call lock, I will give you the iPhone. If you call unlock, you put the iPhone back on the table so that somebody can take it. So lock is a variable that means that only one thread will ever be executing in this region of the code at once. Because if a thread has the lock, no other threads have the lock. Now I need to tell you why this is necessary. So imagine that we are adding up a bunch of numbers. We're adding up a bunch of numbers, diff plus equals something. Okay. Now let's think about how a processor runs. So to add a value, into something in memory, what does a processor have to do? Well, it has to load the value from memory. It loads it into a register. It adds the value to the register, and then it puts the result back. Okay? So imagine that the value in memory was 25. Now, think about one thread or one processor trying to update that value. Let's say I wanted to add 1 to it. I would go to memory, and I would get the value, and I'd bring it back over here to my register, to my processor, and I put 25 in a register. I would add to it. Let's say I add 1, so I make it 26. What? Oh, no, I'm about to go to the device. I'm not on the screen. Okay, it's fine. So that processor has the value 26. Now that processor needs to store the value back to memory. But imagine before that processor stores the value back to memory, another processor comes in and says, well, I need to update diff too, right? Because there are multiple processors running this loop. So it's going to read the value from memory. It's going to store it in its register. It will add some value to it. Let's say it wants to add 2. So now the value is 27. And then it will store the value back to memory. 27. And then maybe a split second later, the other processor stores its value back into memory. And now the value in memory is 26. Now what should the value in memory have been? Should have been 28, right? Because one processor wanted to add 1, another processor wanted to add 2, and this whole program is supposed to compute the overall amount of work that we've added. So if multiple processors are trying to make this update at the same time, some of the processors can the updates can flat out just get lost. So the reason why I need, for this program to be correct, I need this line of code, diff plus equals some value, to be atomic, or it all has to happen. I want the processor to read the data, update the data, and put the data back in memory. before any other processor can read the same value. So that update needs to be all one thing. And so what I did by putting locks around it is I set up a protocol. If you're going to update memory, you need to get the lock. But there's only one lock. So only one thread can have the lock. Maybe I should have used an example which would have been better. Probably would have been my keys. That would have been a better example. Right? So if you want to update the variable, you have to get the keys. You go to memory, you make the update, you put the value back in memory, and then you release the keys. And you release the keys with unlock. And that means another thread can get the keys, do its update, and so on and so on. So the problem that I just described cannot exist if every thread follows the rules of if you're going to update a shared variable, you need to get the lock first. And that's what I was illustrating on this slide. Imagine that two threads want to write to a value that's currently 0. Thread 1 reads the value 0, increments it to make it 1, writes it back to memory to be 1, and in the meantime, this thread read 0, incremented it to be 1, wrote its value back to memory, and now the value in memory is 1 when it should have been 2. So in this example, I used a lock. In other programming languages, you'll see other primitives for you to ensure that things are atomic. So for example, atomic add just says add 10 into this variable and then make sure it's atomic. Atomic says make it atomic. And lock and unlock is a way to make something atomic using locks. So that's why this code was here. Now, does anybody see a performance problem with this code? So let's think about this. All of these threads are running. Everybody's running. And all the threads are running, they're updating their values. And every iteration of a loop, the thread does some math, and then goes to try and get the keys. And when it gets the keys, it updates the diff variable. It updates the diff variable, does its thing, puts the keys back on the table, then does the next element, does some more math to compute the next aij, and then goes back to get the keys. Now, as you can imagine, taking that lock might be kind of expensive. That's kind of like the communication that the students had to do to add up all these numbers. And so taking this lock can very well be much more costly than any of this math. And this part of the program is a part of the program that only one thread can be doing at once. So what did Amdahl's law, or Amdahl's equation, tell us about how much we can speed up this program? If a significant region of the innermost loop is sequential, it means we will not be able to speed this program up very much. So can you think of a change to the program that you can make to make the program still correct, get the exact same value, almost, up to floating point associativity, to be precise, but actually is more efficient? How can we get around, how can we stop having to take the lock on every single element we update? Yes?
Can you put it on any local variable?
Very good. So here's what the suggestion is. The suggestion is, what are we trying to do here? We're trying to compute a sum of all the changes. Well, how about every processor just sit there and add to its own variable every single time? Not writing to diff, but writing to my own version of diff. And then only at the end of the total for loop does every processor take the lock and add it into my diff. So that code would look like this. So I created a new variable here, and there's one of these per thread, because this is an SPMU program. All of this is per thread, except for everything that I put in the fancy plots at the bottom, at the top. So now the processor goes through the whole region. It computes how much its elements have changed. And then only down at the bottom, it will take the lock and update that value. So we've moved from taking the lock for every element to taking the lock once per iteration of the while loop. And we're not too worried about that. So that is a major performance improvement. Okay, so that's good. Now the last thing I want to talk about is what are these barriers? That's other thing in the code that I haven't taught you about at all yet. What do you think these barriers are doing? So these, yeah.
All threads need to reach this point before they.
That's right. So a barrier is another type of synchronization primitive. And what a barrier means is when a thread hits this call, this function call will not return until all the threads have gotten to this call. So another way to think about it is if I had to draw it in pictures, is if I had all of these threads or all of these processors, they're all doing their thing, computing the red cells. And then they get to a barrier and they all wait until everybody's done. So it's kind of like everybody's doing their work, and they get here and they wait for everybody to finish. When everybody finishes, then we keep going again. So that's what the barrier is doing. So there are 3 barriers in this program, which seems a little funny. So I do want you to take, and I want you to take like a minute now and talk over why do all the barriers exist in this code. So take 1 minute, look at this code, and I put 3 barriers in it. And I put 3 barriers in it so that it's correct. So I'll give you 1 minute, maybe 1 minute and a half to think about this. Okay, so if we have 1 minute, let's talk about this. 3 barriers. This is probably the most obvious one. So why does this one exist in the code? And what I mean by that is, if I took it out, because I prefer not to have any barriers, because barriers are just waiting for other people to come, and that's a waste of time. It makes my code slow. But I have 3. So why do I need this barrier? That's right. So if I did not have this barrier, all the threads may not have contributed their differences before I check whether or not we're done. Okay? So that's correct. What about this barrier? What happens if I got rid of this barrier?
sensitive to zero.
That's right. So one thread could say, oh, we're not done yet. I'm going to start again, and I'll start by setting diff to 0, which causes all the other threads to go, oh, we must be done. And then your program is screwed, right? I'll leave the last one for you to think about. And more importantly, can you do better than 2 barriers? In fact, I can do it with 1 barrier and still be correct. It's on the website. We'll talk about it at the beginning of the next class. But see if you can figure out how to do it with 1 barrier and still be correct. Okay, that's all I wanted to talk about today. That's a good job. Everybody's understanding